Okay, today we'd like to talk about relativity, and your job today is very simple. Your job today is simply to derive the equation for special relativity. So, what we have are frames of reference, the spots from which you view your experiment. We had a classical relativity that harkened back to Newton and Galileo. We had this idea of invariance, things that are the same in all frames of reference. We used to think they were mass, time, and distance. We knew that velocity was not invariant, that each person would view the velocities differently depending on their frame of reference. And we also knew that all frames of reference are equally valid. You get the same laws of physics in all your frames of reference, and there's no way to tell if your frame of reference is stationary or moving at a constant speed. Then we saw that if you took the electric constant and the magnetic constant and combined them together in just the right way, you got the speed of light. And the weird thing is, Maxwell seems to show that speed of light is not dependent on your frame of reference. Michelson-Morley tried to experimentally find changes in the speed of light for different frames of reference, and they failed. This seemed to imply that this speed of light is the same for all observers. That even though all the other speeds change, for some reason, the speed of light does not. Einstein made this the crucial part for his special relativity. He said that we have to look at invariance differently than Newton and Galileo. He said, in addition to the laws of physics being the same in all frames of reference, the only other invariant is the speed of light. This leads us to some strange results. The first one was based on a thought experiment. We had a person on a ship and a person on Earth viewing light traveling from the bottom of the ship to the top. And it seems as though, if Einstein is right, and they're measuring the same speed for light, that they must be measuring different times. The reason is they're each going to see the light travel a different distance. So a different distance, but the same speed, implies a different amount of time. So here's what you're going to do today. You are going to derive the equation for special relativity. Start out with this drawing. Put a person on Earth, put a person on the ship, have the ship moving to the right at Vs for the velocity of the ship, have a laser beam being shined straight up as viewed in the ship, from the bottom of the ship to the top of the ship. Then you want to set up 3 different views. The ship view, the Earth view, and then what the ship itself does as viewed from the Earth. Okay? So, the ship view, the person's going to see the light beam travel straight up. The Earth view is going to see the light beam travel on a diagonal. And the person on Earth is going to see the ship travel a certain amount horizontally. So these are your 3 views and the drawing you should have for each. Okay, the Earth view of the light beam is going to be on an angle, so you need to break it up into a horizontal part and a vertical part. The vertical for the ship view, and in fact there only is a vertical, we're going to call that Y. That's the height of the ship. I don't want to call it H because that might get confusing with hypotenuse. So let's just call it Y. The ship itself is going to move a distance X during the time the light is traveling from floor to ceiling. And then we're going to put those into our middle picture. The ship travels X, the light travels Y, but as viewed from the Earth, the light is going to travel along that diagonal, along that hypotenuse. Okay, for all 3 views, we are going to use the simplest of all physics equations. Velocity equals distance over time. We are then going to, for the ship view, realize that the velocity must be the speed of light, because Einstein tells us that this light beam has to travel at a speed c regardless of our frame of reference. For the Earth view, we also see light traveling at the same exact speed. That's why we label it c, a special variable for the speed of light. The distance that the Earth person sees will be the diagonal, so that would be x squared plus y squared. So in addition to simple physics equations, we have one of the oldest math equations in human history. And then finally, we do the ship itself. The velocity is not light, it's the velocity of the ship. If you'd like to, you could call this Vs. Otherwise, V is fine. X, how far the ship travels, and time. Now notice very carefully, this time is the time on the ship, because this was measured by the guy on the ship. These two times are times measured by the person on Earth. And the crazy thing is, time on the ship and time on Earth are no longer invariant. They're different. The Earth person and the ship person see different amounts of time go by on their watches. Okay? Now here's the algebra, and this is what you're going to have to do on your own. I'm going to talk you through it, but you got to turn into me this final piece of work, starting with your picture and all the stuff we did together, and then this new stuff that you're doing on your own. So here's what you need to do. Take this first equation for the guy on the ship, solve it for y, and then square that equation. Same thing over here. Solve it for x, square it. You should now have y squared equals something, x squared equals something, and then plug them in to this middle equation to put all three equations together to make one equation. Okay, once you have that one equation, here's your steps, your algebra steps. You're going to clear the fraction from that equation. You're going to get rid of the square root that still exists in that equation. You're going to get all the terms involving Earth time to one side and all the terms involving ship time to the other. You're going to factor out the Earth time, because the side that has Earth time should have two terms in it. Factor out the Earth time, then solve for ship time. So anything that was with ship time, move it over to the Earth time side. Ship time should be all by itself when you're done. And then finally simplify. You should now have a simple equation, not really simple, but one equation where it will say time on the ship equals something and then Earth time. We'll use this equation tomorrow to see how time is different for these two observers and what the crazy consequences of this are. I know some of you guys have thought about time travel. This will kind of show us how time travel is possible in some ways and not possible in others. That will wait for tomorrow. So good luck. Again, all you have to do is turn into me your work showing the derivation of this new equation.